Welcome back to Lean Together 2025. And I'm very pleased to welcome our next speaker, Scott Carnahan, who's going to tell us about vertex algebras in Lean coming soon.
Thank you. I'm Scott Carnahan. I started doing Lean about a year and a half ago, and it's been quite a lot of fun. So I'd like to start with my main project, which is vertex algebras. So first, I'd like to tell you where vertex algebras appear in nature briefly. So you don't need to know what all these words mean, but I'll just give a quick overview. So first of all, they come up naturally in the representation theory of affine Lie algebras. Affine Lie algebras are central extensions of loop algebras. And so, well, one thing I would like to do is get affine Lie algebras into Mathlib at some point. So the next thing is monstrous moonshine. Monstrous moonshine is perhaps the most famous application of vertex algebras. So there is a vertex algebra, which is let me say this again. There's a vertex algebra whose automorphism group is the monstrous simple group, and it is sort of a relatively natural construction. And the graded traces of elements are genus zero modular functions, so they're somehow very special. And this is this phenomenon was in fact discovered just by some numerical coincidences that appeared. Richard Vertex, who in fact proved the monstrous moonshine conjecture, says that if you're studying the monster and not using vertex algebras, you're basically working with a stone axe. And well, he went on to say that people can do some good work with stone axes. But the point is, if you want to do interesting work with the monster, vertex algebras are a good tool to use. So the next thing is vertex algebras give you a mathematically rigorous part of 2D conformal field theory. So this is a physical theory, but a lot of it is sort of at a good mathematical level. So conformal field theory comes up in some physical phenomena like second-order phase transitions, like if you make water at a suitable pressure and temperature, and also in string theory, conformal field theory comes up. And so next, I would like to tell you a more personal reason why I like formalizing, or why I'm interested in formalizing vertex algebras. So there's a theorem by Huang, Lepowski, and Zhang around 2010. If a vertex algebra satisfies certain technical conditions, which I won't go into, then the category of its modules has a rather natural braided tensor category structure. And so, well, it's a long proof. It's unpublished, and it's about 400 pages. They split it into 8 archive preprints. And I have a paper with Masahiko Miyamoto. It's regularity of fixed point vertex operator subalgebras. And so if you have a rational vertex operator algebra and take fixed points for a solvable group, a finite solvable group, then you get a rational vertex operator subalgebra from the fixed points.
Sorry, I muted everyone, and now I want to unmute you.
Thank you. So this paper that I wrote with him uses this theorem in an essential way, but it has been rejected in part for depending on this result. And so, well, at first my reaction was, I had recently gotten tenure, and I just thought, I don't really need to worry about this paper anymore. But I realized that, in fact, lots of people have been citing it, and so I should probably get something cleaned up in the theory. And so it's not entirely clear that I'll be able to formalize this unpublished paper by Huang, Lepowski, and Zhang, since it is, in fact, 400 pages long. But it would be nice to make some sort of progress. Oops. Next page. Okay, so I'd like to give a quick definition of vertex algebras. If you have a commutative ring, a vertex algebra is a triple. You have a module over the commutative ring, you have a unit element, and you have some kind of collection of multiplications parameterized by the integers. And they satisfy some axioms. So there's a boundedness axiom. U and v is 0 for n sufficiently large, depending on u and v. And there's a unit axiom. If you right multiply by this unit element, then at least if you use the -1 product, you get the identity. And if you use the nth product for n at least 0, you get 0. And finally, there's this Jacobi identity, which is a bit fearsome. It's got lots. In fact, it doesn't particularly look like the Jacobi identity you may have seen if you studied Lie algebras. Well, this is perhaps the biggest hurdle to formalizing. You have to kind of pick a way to talk about the Jacobi identity without actually manipulating these humongous sums. Okay, so I will jump past this Jacobi identity. So what do we need to formalize this? First of all, we have this pair with R module and a unit element. You can just use an additive commutative group and a module structure. And then we have these bilinear product. So we can just write that down. We have some bilinear products, and then we ask that some of them, depending on u and v, we ask that the nth product vanishes for n sufficiently large. And then for these sums, well, we need some kind of binomial coefficients. And so I guess there's an alternative way of formalizing. You can, instead of talking about infinitely many bilinear products, you can talk about one bilinear product that takes values in a formal Laurent series with coefficients in V. And then, well, the Jacobi identity seems to involve composites of these kinds of products, and so maybe you need some iterated Laurent series. I'll say a little bit more about this later. Okay, so the first project that I had to consider was these general binomial coefficients. So at the time I started looking at vertex algebras in Lean, we did not have these general binomial coefficients, so I looked around for ways of formalizing them, or a good theoretical underpinning for this. And so there is a notion of binomial ring, which is just a ring that has a sort of natural choose function. And so you can write it as, well, you have this product x times x minus 1 and so on, and it should be uniquely divisible by n factorial. So this in particular implies characteristic 0. And so my first try was this sort of, well, it's a bit of a mess, really. So I posted this code on Zulip, and I got lots of suggestions about how to improve it. And then I tried PR, and I got lots more suggestions. And so, well, we don't need to really dwell on this particular piece of code, but so the first thing that I should probably point out is there's this exists x in R in this in this part of the class, which well, if you're going to work in Lean, it seems that using an existence statement, especially a unique existence statement, you probably want to just turn that into a function. And so this was something that Junyan suggested on Zulip. And so instead of just having 2 parts of this class, we have 3. Now we have this multi-choose function. And then we have this condition that multi-choose gives you an evaluation of a Pochhammer polynomial. And secondly, well, it's this injectivity is somehow more amenable to further use later on. So we can define binomial coefficients in general using ring choose just as this multi-choose function with a subtraction in it. Okay, so my first try at vertex algebras was the following. We have a parameterized family of bilinear products, and then there's this bound condition. Well, if m is sufficiently large, then this product is going to be 0. And then there's these unit vector conditions that the -1 multiplication on the right by the unit vector gives you identity, and natural numbers give you 0. And then there's this Jacobi identity, which is just a gigantic mess. So um, at the very least, I was able to write down a definition, but I tried to actually work with it, and it turned out to be kind of cumbersome. So there were some problems. First of all, the Jacobi identity was big enough that actually proving anything with it just involved very long proofs. Um, Secondly, I needed to do lots of explicit choice to work with this bound function. If I go back here, this existence of n, I needed a lot of what was this, choose spec or something like that. And finally, in the literature, there's a lot of power series manipulations. And all I'm doing here is looking at coefficients of a power series and translating those kinds of theorems into this explicit coefficient manipulations is very non-trivial. And so I decided that it would be better to develop some API for power series and rewrite the axioms in terms of formal power series. So instead of looking at individual products, U and V, you just package them all into a generating function. And then this boundedness, you can just turn it into a Laurent series condition as long as just using this exponent x to the n minus 1. And then also the Jacobi identity can be split. There are several axiomatizations of vertex algebras. Often there are pairs of axioms which combine to give you the Jacobi identity. So maybe that can be easier. So here's one example. So if you have a pair of vectors in a vertex algebra, then there is some natural number n such that x minus y to the n times, this operator valued series times this second operator valued series is the same thing as x minus y to the n times, these operator valued series, but in reverse order. So if you sort of stare at it for a little while, you might notice that, the left side might be a sort of Laurent series. I guess you would say it's some kind of operator valued iterated Laurent series, first in x and then in y. And the second one is some sort of operator valued iterated Laurent series, first in y and then in x. So in some sense, maybe they live in different places, but you can just look at the underlying coefficient functions and say that they are the same. The second thing is, okay, I'll stop right there. So the proof is if you go to the Jacobi identity and there's this integer parameter t, I'll just go back here. There's an integer parameter t here. Well, maybe I should go back to the non-lean part. So there's I changed the letters. Sorry. Well, there's an integer parameter t. And if you make it big enough, then one side of the Jacobi identity vanishes completely. And then the other sums give you coefficients of these series. And so we would like to make sense of this x minus y to the n times this product of yu, x, y, vy for any integer n. Well, here in locality, you just want natural numbers, but we would like to use it. We would like some invertibility too for later purposes. And so this composite of these two series, these operator valued series, is an R linear map. It takes V to this Laurent series space. And so this target admits a scalar multiplication from this iterated Laurent series ring. And so we would like to expand x minus y to the n there. So if you start composing more and more things, you might find that you're iterating Laurent series many, many times. And so we would like to consider a more general framework using Hahn series. And so in general, if gamma is a poset, a Hahn series is a formal power series with partially well-ordered support. I won't say what partially well-ordered is, but I guess if you have a linear order, then it's just well-founded. So it's the sort of thing that you can do induction on. And if gamma is ordered additive commutative monoid and R is a ring, then you get a ring structure on your Hahn series. And so Laurent series is, in fact, in Mathlib, it's defined as this Hahn series ZR. And you can iterate Laurent series, and you can get, well, it's at least equivalent to Han series on this lexicographic product of two copies of Z with coefficients in R. Now, there's a problem with trying to write everything in terms of Han series, which is that you can get a diamond if you're trying to make modules. So if you have a module RV, you can try to make a module Han series gamma R, Han series gamma V, but then you will get some sort of a diamond if V is equal to Han series gamma R. You can get two inequivalent actions. I guess instances don't like having more than one possible action. And so the solution is to make a type alias. You write Han module and you just define it as Han series. And then you can define your scalar multiplications and module instances that way. Okay, so in order to formalize vertex operators using formal power series, first I define this notion of heterogeneous vertex operators as a sort of general form of left multiplication. This sort of encompasses both normal left multiplication in a vertex algebra and sort of an iterated form. And so you just take any old partial order and you can take a map from an R module to this Han module. And so these have a natural action on the target by Han series. And so that gives us a way of doing a scalar multiplication. And as a special case, we have something called a vertex operator, which is the more traditional left multiplication in a vertex algebra. You can just take this where your gamma is Z, and then your modules are the same. And there's also a normalized coefficient function, which lets you look at your nth product. You just take the x to the minus n minus 1 coefficient, and you call it normalized coefficient. So I should say, so here is one definition of a vertex algebra using power series methods. And so you take, once again, you have a module and you have a product structure. Here, V maps to a vertex operator. Once again, a vertex operator is a map from V to a Laurent series with coefficients in V. So it's like V to Laurent series in V. And then there's these standard unit vector axioms. And then the Jacobi identity has been broken up into this locality statement, and then a statement about a residue product. So I've defined residue products up here. It's a bit complicated. You have to multiply these things in different orders, and then multiply by some integer power of x minus y, and take a residue. But the end result is if you take a residue product of this operator y of u and another operator y of v, you should get the same thing as the coefficient, nth coefficient of yuv. So it's something like being a homomorphism. And so, well, this last axiom is sometimes called associativity, and locality is sometimes called weak commutativity. And so vertex algebras are something like a generalization or a weakening of a commutative associative ring. But I mean, there seems to be a lot more complication there. Anyway, so this is one formalization of vertex algebras. But we're missing a lot of stuff that still needs to be done. So, so if we want to work out the basic theory, we still need to define a lot of stuff with infinite dimensional Lie algebras, like the Virasoro algebra. And so a lot of that theory I still need to put in. And I still need to really write down x minus y to the n in a pretty way. I don't have, haven't really decided on the best way to express this. If we want more advanced theory, this is twisted modules here and intertwining operators and their composites. This doesn't need too much more than the API we already have. We just need Han series with more interesting gamma. And then finally, there's more advanced theory, under certain finiteness conditions, you can write down some correlation functions that live on Riemann surfaces, and they obey some nice differential equations. And there are other constructions that use homological methods. These are things that I am not ready to talk about at the drop of a hat. But anyway, so there's still a lot to do, and there's also if we want to build things like the moonshine module, well, we need some more concrete methods of construction. Okay, so the last thing I really want to say about things I need is this, once again, this binomial to an integer power. I need some good API for rational functions of this form. And one reason is there's a lemma called Dong's lemma for residue products. If you have these sort of vertex operators A, B, and C, then if they are local, that is to say they almost commute up to multiplying by some power of x minus y, then A and this residue product B and C are also local. And the standard proof involves, well, it involves substitutions of the form like x minus z equals x minus y plus y minus z. These are all, very easy to do by hand. But if you try to write this down using the basic elements of Han series, you end up with these sort of huge terms like monomials and 2x if you want to get things right. And so that's a little bit cumbersome. So I'd like to conclude with a few things that I learned. So first of all, definitions are hard to get right. Secondly, it is good to get an early start at defining things, even if they are likely to be bad at first. And third, if you ask a question on Zulip, you might get an answer to a better question that you didn't think to ask. This has happened to me many times, and every time it's just been amazing. And finally, peer review is great for learning good style and new ideas. So if you want to learn, I think, good Mathlib type code, sometimes just tossing out a PR is a good learning experience. And finally, this is something that maybe everybody already knows, but if a proof really seems like a grind, maybe you should try to write some more API. Okay, that is all I have to say. Thank you very much.